Hello, and welcome to HTL Explains with me, Dr. Mario Torres Rodrigo. Today, we're going to be talking about lithium-ion batteries and how batteries that should be flat and functional become this kind of amorphous blob that not only they are not functional, but they can be quite dangerous. So today, we're going to be talking about the risks of lithium-ion batteries. So, if you have been paying attention to the news lately, you might have noticed that there has been an increase in the report of accidents and fires and explosions linked to things such as e-scooters and e-bikes. But also, if you remember from some years ago, you might remember that there was an outrage when certain phones caught fire on commercial flights. And you might be thinking, are these two types of events related? And regarding the title of this presentation, the answer is quite clear. Yes, and it's lithium-ion batteries. So, why are lithium-ion batteries so risky? So, before we get too much into the detail about this, we need to have a bit of a recap from previous videos, and it is about thermal runaways and decomposition reactions. Thermal runaways happen when we have an exothermic reaction, so a chemical reaction that releases energy, that progresses over time. And the accumulation of heat is going to accelerate this reaction even further. To prevent this from happening, normally we have measures such as dissipation or cooling. But if these processes fail, then the chemical reaction is going to get into thermal runaway. And this linked to the decomposition reactions. The composition reaction happen when we have chemical molecules that can break down into different compounds. And the problem with these reactions is that they can also be exothermic. So we have a first runaway event in which our primary reaction is going to be releasing energy and feeding these decomposition reactions that can generate a secondary thermal runaway, and this can be quite dangerous. So what does this have to be with lithium-ion batteries? So if we think of lithium-ion batteries, they are not that different from other types of batteries. We are going to have an anode that in lithium-ion batteries can be, for example, graphite, that is going to store electrons in the graphite rings, and lithium ions that are going to be stored between the layers of graphite. We are going to have an electrolyte, and the electrolyte is going to allow the lithium ion traveling through it, but not electrons. Electrons will have to find another route to get into the cathode, and this secondary route is what is going to be connected to a circuit and is going to be producing the energy that is going to be released from the battery. Finally, we're going to have a cathode that in lithium-ion batteries tend to be a lithium metal oxide, and this is going to store the lithium and the electrons once that the battery has been discharged. Finally, we're going to have also a separator, and the separator is going to be a safety measure. In case that the electrolyte disappears, it's going to prevent short circuit processes happening inside of our battery. So, what does the composition reactions have to be with batteries? So we have that normally the electrolytes that we use in lithium-ion batteries are going to be organic carbonates, such as dimethyl carbonate, ethyl methyl carbonate, ethylene carbonate, propylene carbonate, among others. The problem with these molecules is if we expose them to high temperatures, they can break down, they can decompose, generating CO2, hydrogen gas, and organic gases such as methane, ethane, or propane that can be very flammable. But also the lithium metal oxide can decompose. And in this case, what is going to happen is that the metals such as cobalt oxides can decompose, generating cobalt metal and oxygen. And this links very much with fire risks. If we remember what the three things that we need for a fire or for an explosion to start, we have that we need a fuel, which in this case is going to be provided by the composition of the electrolyte with things such as organic gases and hydrogen. We need oxygen, and the oxygen is going to be provided by the lithium metal oxide decomposition. And finally, we need heat, and the heat is going to be coming from thermal runaway reactions. So we have the three ingredients we have for a fire, making the situation quite risky. But the question that we need to bear in our minds is there a chance that we can produce safe lithium-ion batteries? And the answer is yes. So what are the requirements that a battery needs to meet in order to be considered a good battery and a safe battery? Well, first of all, we need it to be high conductive. So it's going to have a high energy output, but also if we have high conductivity and little resistance, this is going to prevent processes of heating. We need a stable solid electrolyte interface. And the solid electrolyte interface is quite a peculiarity in lithium-ion batteries, in which when the lithium travels through the electrolyte, it's going to chemically react sometimes with the salts in the electrolyte. And when it has traveled through the electrolyte, it is going to precipitate in the interface between the electrolyte, and it's going to generate a crust. And although this can look like a problem a priori, actually what it does is increasing the insulation of the electrolyte even further, helping to generate safer lithium-ion batteries. Also, we need that our salt needs to be thermally stable. We have talked about how the salt can break down into organic gases, so we need to make sure that these kind of processes don't happen in our salt. And finally, we need that our cathode, our metal, are not soluble in the electrolyte, because if we have ionic metals traveling through the electrolyte, that is going to affect the normal functioning of the battery and can result in malfunction. But how do we test for safe batteries? And the answer for this is calorimetry. Calorimetry is a fantastic tool for this. Calorimetry, if you remember, is the science that is going to study the exchange of heat. So how do we apply this to batteries? Well, we are going to have that the batteries are going to react in certain ways when they are functioning, and we need to check for two things. First of all, we need to know that our battery is going to be working safely under normal conditions. So things such as normal use and normal processes of aging. And we have to evaluate that the battery is not going to self-heat to a point that is going to be dangerous. But this is a normal ideal scenario, but we know that batteries are not going to be exposed to ideal conditions. If we have car batteries, they're going to be heated by the car, they're going to be potentially exposed to impacts, they're going to be exposed to punctures, and this can result in internal short circuit that is going to massively affect the normal functioning of the battery. But also we are going to have electrical stress, and despite the fact that manufacturers are providing the instructions for the normal use of batteries, sometimes it can be the case that the battery is going to be exposed to a higher current than it should be, or it can deplete much faster than we had to, or they are going to be charged for longer time than they are supposed to. And this can result in internal short circuits, but also on self-heating. So evaluating the internal short circuit and the self-heating, it is fundamental. And there are going to be two potential outcomes of this analysis. One of them, and that's the scenario that we want, is that the heat dissipation in the battery is going to be higher than the heat accumulation. And that's going to be a safe outcome, and the battery is ready to be used. But also it can be the opposite, and it can be the case that the heating in the battery is going to be higher than the dissipation of heat, and that can result in thermal runaway reactions and in fires and explosions. So to test for the safety of batteries, we have things such as BTC 500 and BTC 130 that are manufactured by HEL. And we're going to have a battery, which is the thing that you can see in the middle of the slide. And we're going to put it in our BTC, and we're going to increase the temperature progressively to see how it behaves thermally. And we can see that on the first stages, the temperature is going to increase, and then the battery is going to stabilize, the temperature is going to increase, and the battery is going to stabilize, and so on and so forth. But then, around 120 degrees, we're going to find that this is not the case. And instead of stabilizing, we're going to have an increase in the temperature. We're going to have self-heating processes, and this is when the battery gets into thermal runaway. And we can see that the temperature in the battery can reach very high values, like 290 degrees. And what happens with the battery when it's exposed to these conditions is that originally it was the picture that we can see on the left hand side of the graph, but then at the end of the experiment it's going to look like that, which is not that different from what we could see here. So what are the consequences of misuse of lithium-ion batteries? Well, between 21 and 22, there was a 28% increase in fires reported linked to lithium-ion batteries. And these fires were linked to poor quality batteries, damaged batteries, and incorrectly used charging devices. And also, Zurich Insurance actually did some research and they found that at least 59% listings online did not comply with the standards. So for example, one of the things they found is that the batteries lacked fuse. And the fuses are going to act as a barrier that is going to prevent further damage. So the take-home messages I want you to go and from this talk and think about is that lithium-ion batteries have huge potential, but also they can be quite an important health and safety risk when they are not up to standard. So in order for us to use these batteries safely, we need to use the batteries following manufacturer's instructions. And this is it from me. My name is Mario Torres Rodrigo, and I'm the applications leader at HEL. If you have any questions, if you have any comments, please just reach out for us. Thank you very much.